All right, so you've heard us talk about it before, but we're going to go into a little bit more detail about the electromagnetic spectrum. Where does energy come from? How do we see light? Like, what is light? And how does light relate to things like a microwave or a radio wave or an X-ray or a gamma ray? Well, to understand that, we first need to understand how we can see normal light. And in general, when we see something, the image is created is made one of two ways. It's made through either light reflecting off of something and hitting our eyes, or when you turn on a light bulb, or when you put energy into a fluorescent, you put electricity into a fluorescent light bulb, that energy gets passed off, that electricity gets passed off as light. So what is happening here? Well, let's look at the Bohr model of an atom to understand. So here I have the nucleus of an atom. This atom has just two energy levels in it. If you recall an energy level is kind of like a floor of a house. And the more energy levels an atom has, the more levels an electron in that atom can occupy. Atoms, or electrons in an atom, in general, want to all be in this lower energy level, but there's not enough room for electrons to fit in this bottom energy level, so the atom creates a higher energy level for these electrons to go to. So, okay, so I've got an atom here, and a little bitty pinpoint represents an electron. And let's just say, I don't know, we're dealing with lithium, element number 3, right? And it has 3 electrons, one in its outermost energy level. But lithium, minding its own business, a ray of energy. Let's call it an X-ray, right? And an X-ray has very short wavelengths, has a very high frequency, and this X-ray just so happens to bump into this electron right here. And this electron doesn't have any say-so in the matter. It gets pushed, it gets booped, if you will. It gets pushed to a higher energy level. So the X-ray is gone. It has exited the picture here. But this energy has to go somewhere. And it goes into this electron, and this electron gets booped in this outer energy level. But just like you and I, when we drink a highly caffeinated energy drink, we get excited. This is what an excited state is called. And before this X-ray hits, by the way, this is called a ground state. Ground state, where the atom, the electrons are all, quote, happy. They're all stable. But here we're excited. And lithium is so excited that it has to do something with this electron. Remember, we all want to be in this lower energy level here. Well, there's one spot now open in this lower energy level, but something has to happen. For every action, there's an equal and opposite reaction. Energy cannot be created or destroyed, so this energy has to be transferred in order for this electron to go back down to where it once was. So, how does that happen? Let's see if I can do this. I can't do that. Well, let's do it this way. Boop. All right, cool. For this to happen, for this electron to go back down to this lower energy level, the atom has to emit light, or has to emit energy, and we see this energy as light. A light wave. That's a very poorly drawn wave, but I think you get it. We'll call this light. Now, some atoms emit visible light when they get excited. Some atoms emit different wavelengths of energy or light that we can't see with our eyes. But this This light that we have here is very specific, by the way, to any atom that we're talking about. Every atom has a very specific pattern of light that it emits when it gets excited. So this brings us now to the visible spectrum. The visible spectrum. We see this light. Humans see this light in the visible spectrum. And the visible spectrum, you might remember this, you might have paid attention, but we've got the red, orange, yellow, green, let's see, blue. I was about to do the wrong one. Blue, indigo, and violet. Roy G. Biv. And so I'll just kind of, it's far more, the colors are not, there's a gradient here, right? The colors sort of, they blend as we go this direction, or even that direction, but I'm just kind of showing you what we humans can see. So, all right, cool. We've got the visible spectrum here. Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Indigo and violet. All right. But this visible spectrum is just a small part of the overall electromagnetic spectrum that we can see. It's a very small fraction of it, actually. So, wavelength-wise, all these, remember, this is all light, and all light behaves, and all energy behaves as a wave. And so there's a wavelength, lambda, for every one of these colors. And in general, the colors range from 700, in terms of wavelength, 700 nanometers, a very small length. We're talking about red. When we get to the green, we're getting closer to about 500 or so. And I'm going to put little approximations here. 500 nanometers. And then on the violet, and the violet side, we've got closer to 400 nanometers. And mind you, you've heard of violet. Well, have you heard of ultraviolet? We can't see ultraviolet, but it is over here. So it's shorter. It's going to be a shorter wavelength because it's on this side of the electromagnetic spectrum. Conversely, you've heard of red and infrared radiation or energy. And it's going to be longer wavelengths. So lower energy and we'll get to energy here in a little bit, actually. But all right, cool. So we've got the visible spectrum, but it's only a very small part. The visible spectrum is only a very small part of the total electromagnetic spectrum. The overall electromagnetic spectrum. The electromagnetic spectrum covers all types of observable energy or radiation that we have. And it goes a little something like this. We'll say that the longest wavelengths of energy are over here, and the shortest wavelengths of energy over here. And remember, since we know that the speed of any energy, c, is a constant, and we know that number is calculated by multiplying wavelength by frequency of any radiation, that if we have a long wavelength here, we'll have a very low frequency. Conversely, on this side, we'll have a very high frequency of radiation. All right, well, and let's draw a little picture here to kind of give you an idea. So long wavelengths and low frequencies and, well, that was bad. That's kind of better. Very short frequencies and very low, very small wavelengths on this side over here. And so there's a continuum that we call it a spectrum, right? But the visible spectrum, the visible spectrum fits into a very small piece of the overall electromagnetic spectrum, or EMS for short. How is it organized? Well, we've got the radio waves here, the things that carry some Wi-Fi signals, literally the radio that you hear in a car. Next up, a slightly higher frequency. We use these to cook our food. I'd love myself some Hot Pockets, some Totino's pizza rolls, obviously when they've cooled off. Or, hey, cell phones. So, radio waves, kind of obvious, but our cell phones, 4G, 5G, operate in this particular part of the electromagnetic spectrum. It's a lower energy level of the electromagnetic spectrum. Then we have, after the microwaves, we have infrared. We talked about that a little earlier as it pertained to the visible spectrum, which is over here. Again, Roy G. Biv again, right? This guy up here. You know what? Actually, let's see if I can't do this. Let's see. We can't just... Can we shrink that down? Nope. Let's see. Copy. Paste. Copy pasta. Right in there. There we go. Cool. So I got my little Roy G. Biv in here again. And remember, we're getting in terms of wavelengths and in terms of wavelengths, got the longer wavelengths over here with the reds, and the shorter wavelengths over here with the violets. After the violets, and infrared, by the way, we use usually for imaging. We also use infrared radiation for cooking things. After the infrareds, we have the ultraviolets. Ultraviolets also used for some imaging techniques. After ultraviolet, we have X-rays. X-rays are very important for looking at material stresses, also medical scans. X-rays are also some of the more important identifiers of our universe outside of Earth. We look at stars in the X-ray spectrum, one of the important ways to look at a star or a planet. And then finally, after X-rays, we have gamma rays. Gamma rays are very dangerous to humans. They do have some practical applications, though. All right, so in terms of energy of a wave, energy of a EMS wave, more specifically, energy of a wave is going to be measured in the joule. You might remember that. Joule is a unit of measurement for energy. Energy of a wave is equal to H times F, where H is something called Planck's constant. This is Planck's constant. Planck's constant. And you're going to find it in your formula chart. But the number, just so you know, is 6.62 times 10 to the negative 34th joule seconds. So that number is constant. And so that means that if we're looking to find the energy of a wave, all we need to know is its frequency. Well, hold on. This tells us something about the electromagnetic spectrum. If I have a very high frequency wave, that means I'm going to have a very high energy wave. On the other end, radio waves, very low frequency, relatively low energy. Right? Okay. We've got the electromagnetic spectrum. We need to pay careful attention to these relationships with energy and frequency and wavelength. We need to know the order that this radiation takes on in the electromagnetic spectrum. And by the way, radiation is not necessarily a bad word. Radiation When you hear radiation, you're probably thinking like cancer or nuclear reactions and things like that. That's what we call ionizing radiation. And ionizing radiation typically finds its way over in this side of the electromagnetic spectrum, more often than not. Okay. One last thing. So, what's like the anatomy? The anatomy of an EMS wave. Electromagnetic waves have two. They're not mechanical, so they're non-mechanical. They don't need a medium to travel through. They're non-mechanical, and that means they're transverse. Spelling is tough. Transverse. Oh my doodles. There we go. So they're non-mechanical, they're transverse. And here's in general what they will look like. So if I have a transverse wave here, and it's traveling in this direction, we live in a three-dimensional world. Well, electromagnetic waves take on a three-dimensional three-dimensional property. So we first have we'll call this there's two fields. Two fields. There's the electrical field carried in an electromagnetic wave, the electrical field that's created by this transverse wave. And then there's let's do it in red. There is another component to this wave. Remember, it's called the electromagnetic spectrum. Well, there's a magnetic component to this. And the electromagnetic component the magnetic component to an electromagnetic wave is it operates perpendicularly to this electrical component of the wave. So, all right, I got to figure out how to draw this. You're seeing me struggle live and in person with this. So let's see. So imagine this is 3D. You art students are gonna love the drawing of this. Yeah, so close enough. There is, imagine, you're going to have to use your imagination a little bit, that this magnetic portion is pushing out to the left while this is the magnetic field is pushing out perpendicularly to the electrical field. So if the electrical fields move up and down, the magnetic fields are going to operate left and right in a three-dimensional plane in the electromagnetic spectrum. So that's an important note to write down. Magnetic fields are perpendicular to electrical fields. All right. So yeah, that's the gist of electromagnetic radiation and the spectrum itself. So again, we have when elements get excited, they emit a wavelength of energy, and we can sometimes see this energy as visible light. Other times we might not, but that doesn't mean it's not there. It may take the It may take the form of different types of electromagnetic radiation, some with lower frequency and lower energy, or some with higher frequency and higher energy. And don't forget the relationship of wavelength to those frequencies. And then in terms of a single transverse wave of electromagnetic radiation itself, there's two primary components, an electrical component and a magnetic component.